Yesterday, we worked with geometric vectors, where we just look at a picture of the vector and we see the magnitude and direction from there, and we can put on a grid and count the magnitude and direction. We can also talk about algebraic vectors, where we put specific numbers on these vectors, and we don't need a picture to have an algebraic vector. There are a couple different ways to write algebraic vectors. If I have vector v, it can be written with these arrow brackets as a comma b, where the a and the b are real numbers called scalars, and they are called the components of vector v. You can use those brackets, or you can use what's called component form. When you use component form, we talk about I hat and j hat, and in your book, these are just bold I and bold j. The I hat represents one unit in the positive x direction. J hat represents one unit in the positive y direction. So I can write a vector algebraically as either a comma b inside of the pointed brackets, or as a times I hat plus b times j hat. Here's an example. If I want to write vector v, if I go to this picture and I look at v, I'm going to count. V goes 1, 2, 3, 4 to the left. So it goes -4 in the x direction, and it goes up 1. And make sure you're going from the initial point to the end. Always go in the direction toward the arrow. So it goes 4 to the left and 1 up. I can write that as the x component is -4 and the y component is 1. Or I can use my component form, -4 I hat plus 1 j hat, or just plus 1 plus j hat. If I look at u, again, start at the beginning, look at the x direction first. U goes 1, 2 to the left, and then it goes 1, 2, 3, 4 down. So my x component is -2, and my y component is -4. In other words, I could also write this as -2 I hat minus 4 j hat. W goes 1, 2, 3, 4 to the right, and then up 2. So it has positive x and y components. It goes 4 to the right and 2 up. 4 I hat plus 2 j hat. The algebraic form allows us to do calculations more quickly. The other thing we can do when we have an algebraic vector is find the magnitude of the vector using a calculation. We know that magnitude of the vector is the length of the vector. And so if I have a vector, and I break it down into its components, it's going to go over A and up B when we write it in the component form, A comma B. The magnitude, and the symbol that's used for magnitude is double lines on each side of the vector name. This is like an absolute value symbol, only with 2 on each side. The magnitude is the length of this vector. Well, if we have the x and y components, we have the length of the legs of that right triangle. Legs squared plus legs squared equals hypotenuse squared. The way that we find the magnitude of the vector is to take the square root of each side of this equation. Magnitude of the vector is equal to the square root of a squared plus b squared. You should feel like the calculations throughout this whole chapter are very similar. We were finding the magnitude of a polar form of the magnitude of a complex number in section 9.3. We were finding the radius when we went to polar form in 9.1, and all of those involved finding the length of this hypotenuse of a right triangle where you had x and y components. So the calculations are all similar. So for example here, I'm not going to count my length here, but I have a vector that starts at -1119 and goes to 1524. To find its x component, I need to take the final x minus the first x. So it's 15 minus -11, so that's 26. And my y component is 24 minus 19, which is 5. The component form for vector D is 26 I hat plus 5 j hat. And just check and make sure your answers make sense. This is going to the right 26 and up 5. That's a reasonable answer. If I want to find the magnitude of D, I would take the square root of a squared plus b squared. And for these, you're going to try and get them into simplest form, and you can use your calculator. 26 squared plus 5 squared is 701. The magnitude of this is the square root of 701. Now, vector E, I don't need to do any calculations to find its component form because it's starting at the origin. So if it starts at the origin and ends up at -10, -25, it must be going left 10, so -10 I hat, and down 25, minus 25 j hat. And then when I go to calculate the magnitude, it's square root of 10 squared plus 25 squared. You can put the negatives in here, but you know that squaring -10 gives you the same thing as squaring +10. And when I add this up, I get the square root of 725. 725 is 25 times 29, so this is 5 times the square root of 29. One more to find vector F. It goes, again, I start at 3, 8, and I end at 20, -22. I'm starting at 3 and ending at 20. I'm going to the right by 17, and I'm going down from 8 to -22. If you can't figure it out in your head, take the final y minus the initial y, and you get that this is minus 30 j hat. Magnitude, square root of a squared plus b squared, which is the square root of 1189, which I'm going to leave just like that. One kind of generalization here, if you have a vector that goes from the point x1, y1 to the point x2, y2, and again, the arrow tells me which is the starting and which is the ending point, I can find the x component. Think about this point here, it has the coordinate of x2, y1. I can find the x component, how far it goes in the x direction, by taking x2 minus x1. I can find the y component by taking y2 minus y1. So this vector would be x2 minus x1 I hat plus y2 minus y1 j hat. And if I wanted to find the magnitude of that vector, the formula is square root of a squared plus b squared. And this should look like something you've seen before. This is distance formula. It's the same exact formula because you're doing the same thing. Distance formula gives you the distance between 2 points anywhere on the coordinate plane. Magnitude of a vector is the length of the segment joining those 2 points on the coordinate plane. So it should look very similar. You're going to do some algebraic calculations with vectors today, and then we're going to do one more day of vectors next week before we do a little review and a quiz on 9.3 and 9.4.